This is a revision video for P6g Transformers and their uses. Step-up transformers are used to increase the voltage from the generators at a power station. The power is transmitted at a high voltage over the national grid. At electricity substations, the voltage is then reduced by step-down transformers for use in homes, shops and offices. Some power is wasted as heat. The current flowing through the cables has a heating effect, and the transformer also heats up slightly. Transformers work by using two ideas. 1. That electric current can produce a magnetic field. This is the motor effect. And 2. That a magnetic field can produce a voltage. This is the dynamo effect. They are used to change the size of an alternating voltage. This is how a transformer works. The primary coil is connected to a power supply. The current flowing through the primary coil sets up a magnetic field that runs all the way around the core. The iron core then becomes magnetised, and the strength of the field is greater. If the current is an alternating supply, the current and the magnetic field change continuously. This has the same effect as moving a magnet in and out of a secondary coil. An alternating voltage is set up between the ends of the secondary coil, and when the coil is connected to a circuit, a current flows. A transformer works only when an alternating current is supplied to the primary coil. If a direct current were to be used, the magnetic field in the core would not change, and there would be no effect in the secondary coil. Remember that the two coils are not connected electrically, so no current flows between them. There is no current flowing through the iron core, only a magnetic field. In a step-up transformer, the secondary coil has got more turns. The voltage across the secondary coil is greater than the voltage across the primary coil. It has been stepped up. In a step-down transformer, the secondary coil has fewer turns. The voltage across the secondary coil is less than the voltage across the primary coil. The voltage steps down. The voltage across each of the coils is related by this equation. The voltage across the primary coil divided by the voltage across the secondary coil equals the number of turns on the primary divided by the number of turns on the secondary coil, or Vp for primary divided by Vs for secondary equals Np for the number of turns on the primary divided by Ns for the number of turns on the secondary. This is an example of how to apply this equation. The transformer has 100 turns on the primary coil and 1500 turns on the secondary coil. The voltage across the primary coil is 300 volts. What is the voltage across the secondary? So if you start by writing down your equation, then you can start putting the values in. So here we've got 300 volts on the primary, divided by the voltage across the secondary, because we don't know that yet, equals 100 for the turns on the primary coil and 1 divided by 1500 for the number of turns on the secondary coil. So if you put those numbers in and do that calculation, you end up with a voltage of 4500 across the secondary coil. Here's an example for you to try. You've got a primary coil of a transformer with 200 turns, and the main supply is 230 volts. What is a suitable number of turns on the secondary coil for a laptop needing a supply of 11.5 volts? If you stop the video now, you can have a go at this equation and putting the numbers in. Okay, so here we've got the solution. The voltage across the primary is 230 volts. The voltage across the secondary is 11.5, and that equals to 200 divided by the number of turns on the secondary coil. If you rearrange that, you can see that this is a step-down transformer and the secondary coil should have 10 turns. If you stop the video again now, there's some more questions for you to try on practicing that equation. If you can't remember what the equation is, then go back and write it down. Right, we're now going to talk about the uses of transformers. The main supply in the UK is 230 volts. Some devices need transformers to alter the voltage from the main supply to a lower voltage. These include things like laptops, phone chargers, battery chargers, TVs and computers. Some circuits have to use something called an isolation transformer. With an isolation transformer, there's no direct link between the current that flows through the device and the main supply, so they are safer. Things like shavers use this kind of transformer. Isolation transformers have equal numbers of turns in their primary and secondary coils, so they do not change the voltage. As the link is only through the changing magnetic field, there is less chance of an earth wire touching live parts. They can also be used for computers and sensitive lab equipment that needs protecting. Transformers make up a big part of the national grid. Transformers step up the voltage and decrease the current on the main grid wires. They then have to step down the voltage and increase the current for business and domestic uses. Some power is wasted and lost as heat. The current flowing through the cables has a heating effect, and the transformers also heat up. Whenever electrical energy is transmitted, there's always a power loss. So it's not just happening in transformers, it's any place where you've got electricity being transmitted. The equation you need to use for this power loss is power loss equals current squared times the resistance, or P equals I squared times R. In order to reduce this power loss, you need as small a current as possible, because it's the current that produces the heating effect. Remember that this is related to the equation power equals voltage times current. Here is an example of how to use that equation. How much more power is lost in a circuit with a current of 2 amps than a circuit with a current of 0.5 amps? The resistance in the circuit has not changed. We know that P equals I squared times R. So the power loss in circuit 1 is equal to 22. And this means that the resistance is 4R. The power lost in circuit 2 is 0.5 squared, and this equals to 0.5R. So there's 16 times more power lost in the first circuit. We saw this equation before, that power equals voltage times current, and this equation can also be used for transformers. The power in the primary coil is equal to the voltage in the primary coil times the current in the primary coil. You can also see that the power in the secondary coil is equal to the voltage across the secondary coil times the current in the secondary coil. And if you assume that the power in the primary coil is equal to the power in the secondary coil, then you can put these two equations equal to each other. Here is an example of how to use this. Calculate the voltage across the primary coil of a transformer when the current through the primary coil is 2 amps, the voltage across the secondary coil is 230 volts, and the current through the secondary coil is 14 amps. So we start by writing our equation down, and then we can put the numbers in. So voltage across the primary times 2 equals 230 times 14. If you do that rearranging, you can find out that the voltage across the primary is equal to 1610 volts. And that brings an end to this revision section on transformers and uses of transformers. If you stop the video now, there's some more practice of questions that involve using those equations.